Nestled in the vastness of space, Earth is more than just a blue marble floating in a cosmic sea. It is enveloped by an invisible shield known as the magnetosphere, a magnetic bubble that plays a crucial role in protecting our planet from the relentless barrage of solar radiation. But what exactly is the magnetosphere, and how does it safeguard life on Earth? Join us as we delve into this enigmatic shield, exploring its structure, function, and the vital role it plays in our daily lives. The magnetosphere is not merely a simple protective layer. It is a vast, dynamic region that extends far beyond the surface of our planet, reaching thousands of kilometers into space. It is shaped by the complex interplay between Earth's magnetic field and the solar wind, a continuous stream of charged particles emitted by the sun. This solar wind is composed mainly of electrons and protons, traveling at high speeds, and it plays a significant role in shaping the environment around our planet. The magnetic field itself is generated by the motion of molten iron and nickel in the Earth's outer core, creating a dynamo effect that produces a magnetic field strong enough to influence space weather. This magnetic field takes on a unique shape, resembling a teardrop, with a bulging side facing the sun and a long tail extending away from it, known as the magnetotail. The magnetosphere is structured in several distinct regions: the bow shock, magnetosheath, magnetopause, and the magnetotail, each with its own unique characteristics and functions. The bow shock is where the solar wind slows down abruptly as it encounters the magnetosphere, creating turbulence and complexity. The magnetosheath is the region between the bow shock and the magnetopause, where solar wind particles become mixed and interact with the magnetic field. At the magnetopause, the boundary between the magnetosphere and the solar wind, the magnetic forces balance the pressure from the solar wind. This region can fluctuate in size and shape, responding to solar activity and varying conditions in space. The magnetotail, on the other hand, stretches far into space, with its length influenced by solar wind conditions. This dynamic and multifaceted structure is crucial for maintaining the conditions necessary for life on Earth. When the solar wind reaches Earth, it encounters this protective shield. Instead of bombarding the planet directly, the magnetosphere deflects most of the solar wind, guiding it around our world. This interaction creates a phenomenon known as the bow shock, a turbulent region where the solar wind slows down and becomes chaotic as it meets the magnetosphere. Most of the charged particles are diverted, but some manage to breach the magnetosphere, particularly near the poles where the magnetic field lines converge. This region, known as the auroral oval, allows solar particles to enter the atmosphere. Here, they collide with atmospheric gases, resulting in the awe-inspiring light displays known as auroras, natural phenomena that transform the polar night sky into a vibrant canvas of color. But the beauty of the auroras is merely a byproduct of a much more critical function of the magnetosphere, shielding us from solar and cosmic radiation. These energetic particles can cause significant harm to both technology and living organisms, making the magnetosphere's role as a protective barrier absolutely vital. Without this shield, the harsh conditions of space would present serious challenges for any form of life. The particles that breach the magnetosphere can induce electrical currents in the atmosphere, leading to phenomena like geomagnetic storms. These storms can disrupt electrical grids, navigation systems, and communications, illustrating just how interconnected our technology is with the natural protective mechanisms of our planet. These breathtaking auroras, commonly referred to as the northern and southern lights, are a testament to the magnetosphere's complex interaction with solar radiation. When solar wind particles penetrate the magnetic shield and enter the atmosphere, they excite atoms of oxygen and nitrogen, causing them to emit light in various colors. The stunning visual display serves as a reminder of the delicate balance between solar activity and Earth's protective shield. However, the magnetosphere's role extends far beyond creating these spectacular light shows. It serves as a critical barrier against harmful solar and cosmic radiation, shielding life on Earth from the potentially devastating effects of high-energy particles. Without the magnetosphere, Earth would be bombarded by intense radiation, making it nearly impossible for life as we know it to thrive. Studies have shown that planets lacking a substantial magnetic field, like Mars, are more vulnerable to radiation exposure, which contributes to their inhospitable environments. Mars, once thought to have conditions suitable for life, lost much of its atmosphere due to the absence of a protective magnetic field, resulting in a barren landscape exposed to harsh solar and cosmic radiation. The threat posed by solar radiation cannot be understated. High levels of radiation can disrupt satellite operations, interfere with communication systems, and pose risks to astronauts working beyond the magnetosphere. Space missions that venture outside of this protective bubble, such as those to the Moon or Mars, require careful planning to mitigate radiation exposure. Astronauts aboard the International Space Station, ISS, are continually monitored for radiation exposure as they spend extended periods in low Earth orbit where the magnetosphere's protective effects are diminished. Radiation exposure can lead to serious health risks, including increased cancer rates and other long-term health complications. Moreover, without this protective shield, life on Earth would face unprecedented challenges from solar flares and cosmic rays, leading to increased radiation exposure that could endanger living organisms. The magnetosphere is particularly vital during solar events, such as solar flares and coronal mass ejections, CMEs, which release enormous quantities of energy and charged particles. When a solar flare or CME occurs, the magnetosphere can become temporarily overloaded, leading to geomagnetic storms. These storms can disrupt power grids, impact satellite communications, and even affect navigation systems. As the solar wind interacts with the magnetic field, it can induce electrical currents in the Earth's surface, potentially causing voltage surges that affect infrastructure. For example, the 1989 geomagnetic storm caused a blackout in Quebec, Canada, leaving millions without power. Similarly, the 2003 solar storms disrupted satellite communications and GPS services worldwide. Scientists continuously monitor solar activity using satellites like the Solar and Heliospheric Observatory, SOHO, and the Advanced Composition Explorer, ACE. These spacecraft provide crucial data on solar winds and magnetic field fluctuations, helping researchers understand how to predict and mitigate the effects of space weather on Earth. The relationship between the Sun and the magnetosphere is dynamic and complex, demanding our attention as we navigate an increasingly technology-dependent world. The study of geomagnetic storms has become increasingly important, especially as our reliance on technology grows. From GPS navigation to telecommunications, understanding and predicting solar weather is essential to safeguarding our infrastructure and ensuring the safety of those who venture into space. Understanding the magnetosphere is crucial not only for protecting Earth, but also for advancing our exploration of space. As humanity ventures further into the cosmos, knowledge of magnetic fields and their interactions will be essential for safeguarding astronauts and spacecraft from the dangers of solar radiation. Researchers employ advanced models and simulations to study the magnetosphere's dynamics, aiming to improve our predictive capabilities for space weather events. With missions like NASA's upcoming IMAP, Interstellar Mapping and Acceleration Probe, set to launch, scientists hope to uncover more secrets about the interactions between solar wind and our magnetic field. This mission will not only enhance our understanding of our own magnetosphere, but also provide insights into the magnetic environments of other celestial bodies, paving the way for future exploration. Furthermore, understanding the magnetosphere has implications beyond Earth. By studying the magnetospheres of other planets, such as Jupiter and Saturn, we can gain insights into the conditions that support or inhibit the development of life. The knowledge gained from studying Earth's magnetosphere can help inform our understanding of exoplanets and their potential to host life, as magnetic fields play a critical role in protecting planetary atmospheres. As we reflect on the enigmatic magnetosphere, we are reminded of the intricate balance that exists within our solar system. This invisible shield, forged by the planet's magnetic forces, plays a pivotal role in protecting life on Earth from the harsh realities of space. It is a reminder of the delicate interplay between our planet and the cosmic forces that surround us. The magnetosphere is not just a protective barrier. It is a dynamic system that influences space weather and plays a crucial role in the overall health of our planet. With ongoing research and advancements in technology, we continue to uncover the mysteries of this essential shield, deepening our understanding of Earth and its place in the cosmos. As we continue to explore the universe, the magnetosphere stands as a testament to the power of nature and the importance of understanding the forces that shape our world. Each new discovery brings us closer to unraveling the mysteries of our magnetic shield and the solar system as a whole. What other secrets does the universe hold? What new challenges and wonders lie ahead in our quest for knowledge? The journey to unveil the secrets of the universe has only just begun.